Lesson 64, moving with Newton's third law. We will discuss how movement works with Newton's third law. This is sort of a continuation of yesterday's lesson, which was just trying to wrap up Newton's third law. And I'm going to talk about that in a sec. So the main thing that I wanted to talk to you guys about today was movement and how movement can be affected by this kind of thing, by Newton's third law. But we've already sort of briefly touched on it, but I wanted to spend a little bit more time talking about it. So let's go. Last time I had you guys, we talked about the, firstly, let's go back all the way here, all the way to Tuesday's lesson, where we talked about Newton's third law. Newton's third law is if you push an object, it will push back on you. Because every force, every action force, there's an equal and opposite reaction force. Now, we said, so therefore, because every force has an equal and opposite force, you can think about them as working in pairs. If the paperclip is pulled towards the magnet is pulled towards the paperclip. And then we said here are some action-reaction pairs. But the important thing is they must act on different objects. Again, I know you're sick of this, but now I can draw quickly because I have my pen. You've got the force of the normal force, and you've got the force, you got the normal force acting on the apple, and you've got the gravitational force acting on the apple. Now, those are not action-reaction pairs, but the normal force of the apple pushing down on the table, those are action-reaction pairs. These two are action-reaction pairs because they're acting on different objects, they're the same size, they're in opposite directions. That's what you need to look at when we look at the action-reaction pairs. We did some stuff about elevators, and which again was related to action-reaction pairs. And we said that this force, that these two are not action-reaction pairs. This force here is actually made up of two forces. One, which is the force of the normal force, which is still 700 newtons, but also this 142 newtons, which is the elevator getting pulled down. So it's whatever is pulling the elevator down or pushing the elevator down. And so that's why that force is there. We did some more elevator stuff. Then we wrapped up by talking about the problem with mass is this. If I hit a ball, if I've had to hit a baseball and I had to hit a bat with the same, they should experience the same force. But the answer to this was, so why doesn't the bat go flying backwards? The answer to that is got to do with they both experience the same force, but they have the same force, but they experience it differently. What do I mean by that? Well, it's got to do with acceleration. The force might be the same, but the mass of the ball is a lot smaller than the mass of the bat. So therefore, the acceleration of the ball will be a lot larger than the acceleration of the bat. And so therefore, that big acceleration means that ball is going to go flying really quickly, whereas the bat is only going to be moving a little bit backwards. I then hit you guys with a different interpretation of Newton's third law. When two objects interact with each other, there's an equal, the same force experienced by both objects, but they accelerate differently. The reason they accelerate differently is because of Newton's second law. They accelerate depending on their mass. So then I showed you guys, and this sort of applies to today's lesson, by the way, that the reason we're able to walk is that we push backwards on the ground, and that forces our foot upwards to the right. Now the ground doesn't move very much because, again, the mass of the earth and the ground is huge. And also there's other forces in play. I keep saying that. So that force mass is huge, but the mass of a human in comparison is very, very small. So we experience a larger acceleration. That acceleration is going to be forward, which means that's how we walk forward. We push backwards on the earth. You might be able to tell when that this is the case is if you ever tried to walk on slippery ground, or if you've ever tried to run somewhere in your socks. What you might find is that you push backwards on the ground, but because you don't have friction, you don't experience that force forward. And so instead, you don't move anywhere. We then did this example here, which I then gave you guys, and about half the class got it wrong, even though I had just explained it. When a firefly hits the window of the bus, they both experience the same force. I said, this is a trick question. Which of the two forces are greater? Neither. They are both the same force. The only difference is the firefly is a very, very small mass, whereas the bus has a huge mass. The acceleration by the bus, whatever, it's going to be very, very small, whereas the acceleration by the fly is going to be huge. I said for an example, let's do an example. Let's say that they both experience 100 newtons worth of force. The fly is probably going to be 0.0. It's going to be about maybe, I don't know how much a fly is going to weigh. Probably more like 100th of a gram. Yeah, we'll go with 100th of a gram. So therefore, actually that's going to be one. This is in kilograms. So we've got to go 0.00. There's 1 gram. 0.001. That's 1, 2, 3, 4, 5, 1 to the power of -5. Whereas a bus is probably going to be about maybe 10 tons, so we'll go with 10,000. That acceleration is going to be 1 over 100. It's going to be 0.01 meters per second squared. Whereas the acceleration of the poor little firefly, that's going to be that's 1 times 10 to the -5. We'll go, that's 1 times 10 to the 2. That's going to be 1 times 10 to the 7 meters per second squared. That, I may have got that wrong, but you know, so you can see which one's going to be much larger. But the force is the same. That's what I was trying to get across. Today what we're going to talk about is going to talk a little bit more about movement. We've got another one of those examples, and then that's going to be it. So let's power through quickly. This picture I wanted to talk about with regards to movement. Here we've got a rower. Now the rower, what happens with the rower is the rower pushes backwards on the water. And as the rower pushes backwards on the water in turn pushes forward on the boat, which overall that will make that canoe or rowboat go a lot faster. It'll make it push forwards. The advantage with, I love using rowing as an example, is because when you row or when you swim, you actually see the water that you're pushing backwards go behind you. And that's what happens. You actually see it get forced backwards. Another example is in a rocket ship. If you see a rocket is going to push out flames. Flames should be what? Maybe orange here. From the bottom of a rocket. As that pushes the flames downwards, that forces the rocket upwards. And that's why you get the rocket is able to be propelled into the air. So yeah, that's the same sort of thing. And the last one, I guess, example would be something like, I don't know, a plane. A plane has air turbines. And what the air turbines do is they suck in air, and then they push the air out backwards. And as that air gets pushed out behind it, it actually then pushes the plane forwards. And so here are three ways in which movement can be happening. The first one, we're pushing water. The second one, we're pushing hot gas. The third one, we're pushing air. The other one about pushing hot gas is the hot gas also expands because it's hot, which further pushes it. That's why explosions allow for a lot more movement, because as it expands out, that will mean that it's pushing against the air. So that's going to push against you as well. So that's sort of two examples here. Well, that's actually three examples in one. We've got pushing against water, pushing out, pushing something out, and pushing against air. When you push something out as well, you can also think about other things. You might be like, oh, well, what if I fill the bottle? What if I had a water bottle? What about instead of hot gas, what if I used a bottle with water? And I, forced water out of the water bottle? Well, that's going to do the same thing. That's going to propel it upwards. What if instead of a water bottle, what if I used a balloon? And then I pushed air out? Well, guess what? As the air comes out, that's gonna push the balloon upwards. And that's why if you fill up a balloon and you let it go, it goes and just flies around and lands somewhere. That's the air is being pushed out, and that will push that balloon forwards. There you go. There's now we've got 1, 2, 3, 4, 5 examples of Newton's third law straight away, right there. And all of these are good examples of Newton's third law, but they also all tie in with movement. They all tie in with how do human beings, how do we harness Newton's third law in order to get an idea of it. Wanted to talk about one more. Well, let's do this one here. So here's some examples of Newton's third law, some more examples. We've got swimming, which is what we just did. Your hand pushes back on the water, and so the water pushes forward on your hand, and that pushes your hands attached to your body, so that allows you to go forwards. Here we've got the one that we just talked about, aircraft and rockets. Hot gases push backward, the gas pushes forward. But here are three that we didn't talk about. Jumping, as your legs push down on the earth pushes up on your legs, and that allows you to go into the air. A car, instead of the foot that we had the picture of, where the foot pushed down onto the earth, and so the earth pushed up on the foot, if you replace that foot with a car tire, all the difference is the car pushes backwards on the earth, because as it spins, it pushes backwards on the earth, and so that pushes the earth pushes forward on the car. That also applies to bicycles as well. And the last one is skydiving. The gravitational force of the skydiver, as you jump out of a plane, gravity pulls you down, but you will also pull the earth up. The force of gravitation on the earth from the skydiver. So we've got now 3 more examples about how something can move when it, these are just some more examples of how Newton's third law exists in movement. I'm going to sort of pause here for a second, just to give you guys a quick moment here, just to understand one thing here. I'm giving you examples. The reason I'm giving you so many examples here is just because the amount of times I've seen in tests give an example of Newton's third law, and students just go, I don't have anything. Or give an example of Newton's first law. So many science tests in chemistry, in physics, they all have this same idea. Give an example of this law. So I'm trying to give you a bunch of examples so that you're a bit familiar with them. I'm also trying to give you these examples so that if you ever see, oh, A bicycle is, going down a hill. It pushes backwards, you go, bicycle. It's going to be pushing backwards. You have got something in your mind. But then again, like, I could replace a lot of these things with different ones. I could replace the jumping one with a spring, but you guys should maybe, if you've got the skill, be able to go, oh, it's pushing down in the earth the same way as how if I want to jump from the air, I push down the earth. So just more examples are always a good thing. The last thing I wanted to do is I wanted to hit you with this, and I wanted you to see who can guess it. And I'm going to open this up to getting you guys to answer this in chat in a fraction of a second. You can answer privately if you want, but that's fine. I won't, and this time I won't point it out. Many people are familiar with the fact that rifles recoil when fired. That a rifle recoils when fired. If you don't know what a recoil is, that's if you've got a gun and you shoot a bullet, that gun will go backwards a bit. So it'll sort of move backwards when you shoot the gun. A gunpowder explosion creates, the recoil is the result of the action-reaction pairs. Yeah. So as that bullet gets pushed forward, the gun forces the bullet forwards. The bullet will force the gun backwards. Now, a gunpowder explosion creates hot gas that expands outward, allowing the rifle to push forward on the bullet. Consistent with Newton's third law of motion, the bullet pushes backwards on the rifle. The acceleration of the recoiling rifle is, and here is the question, the acceleration of the recoiling rifle is greater than the acceleration of the bullet, smaller than the acceleration of the bullet, the same size acceleration of the bullet. So I'm asking about the acceleration. Is the movement backwards by the gun the less or A, B, or C? I've got one guess, and this person's kept it private, so I'm not going to say who it is, but they've guessed B. I've got a public guess from Kelvin for C. I've got another private guess for B, so I've got 2 answers for B, 3 answers for B. Thank you, Arn. Let's see if I can get maybe 8 people to respond. So I've got 4. Let's get 4 more responses before I give the answer. I've got an answer of D, which is not one of the ones on there. Phoenix, thanks for that. Can I get a couple more responses? What do we think? I've got 5. We've got another response for another answer for B. Give me 2 more. Like 3 more would be great, but 2 more will be fine. Give me someone else. Someone else. You can do it privately. I've got A. I've got D from Vince. Thanks, Vince. Thanks, Phoenix. You kind of ruined it. Let's just go with that then. One more. Let's just do one more. Can you get one more answer? A, B, or C? What are people thinking? One more. Okay, I've got another answer, and it was C. So let's look at this now. Here's the thing. So, which of these is true? Firstly, no one said A. So here's the thing. We know that the force on the bullet and the force on the gun are the same. They are equal. They might be going in opposite directions, but they are equal. But the mass of the bullet is very small. Let's call that let's call it like 10 grams. So let's call it 0.1 grams. Whereas if the force on the gun, the gun's going to weigh maybe 1 kilo, maybe 2 kilos, maybe a kilo. We'll go with 1.5 kilos. So 1.5. Doesn't matter what number is on top. This acceleration, because A equals the force divided by mass, this acceleration is going to be lower because this number is larger. So the acceleration is going to be smaller. So the acceleration of the recoiling rifle is smaller than that of the bullet. And that should be obvious as well. You know that bullet is going to fly out at a blisteringly fast speed, but that recoil it's just not going to be as fast. If it was, you wouldn't have guns. You wouldn't be able to use guns because every time you used a gun, the gun would fly backwards at the same speed as the bullet, and then you would end up, you could get killed at the same time as using a gun. This is one of the initial problems that they had when they used like cannons, essentially. You got a cannon and you fire that cannon, the cannonball comes out, but that block will go backwards. So you're going to make sure that when you fire a cannon that you're not standing behind it because it's going to fly backwards. And so that's why the answer is B and not C. The people that guess C, I can see why you guessed it, because you've gone, oh, I've just been fooled by Mr. Greer in example 1 for trying to confuse me and get with the force. No, I know the force is the same, so therefore it has to be C. And you've gotten confused again. Yes, the forces are the same, but the accelerations are different. So that's what I wanted you to pay attention to.